All right, so yesterday we did a patty paper activity. And what was the whole point of doing the patty paper activity? We're taking functions, and what were we doing to those functions? We were looking for what was known as the inverse. And what geometrically were we doing when we were taking the inverse of a function? We were reflecting the original graph across the line y equal x. The resulting graph, the image of the graph reflected across y equal x, is what's known as the inverse of the graph, the inverse of a function. And we also noticed that not all relations had inverses that were also functions, right? And so we're going to talk a little bit about that. We're going to formalize everything that we did yesterday to make sure that we can do the algebraic process that underlines it. So if you recall, when we were first being introduced to functions, we first said that, well, they're all relations. And a relation is just a mapping of input and output values. And some relations are functions. And how could we tell by looking at the graph if the given relation was a function? If it passed the vertical line test. If I could not draw a vertical line and pass through the graph more than once, meaning every x value has one and only one corresponding y value. So we are given relations, and we are taking the inverse of these relations. And if, let's say you've been given a table of values. So this is our, keep going. Heaven help me. So here is my original relation. Now, by looking at this table of values, the input values and the corresponding output values, is this relation a function? Yes, it is, right? Every input value has one and only one output value. So if I wanted to plot those points and graph it, I don't really know what it looks like unless I can write an equation, and it's an equation that we've seen before. But if I just were given this table of values and I said, gosh, I wonder what the inverse relation would be. Well, how would we do that? Yesterday, what did we do to get the inverse? Given a table of values, what did we do?
You switched the line.
That's right. We took all our domain values, our input values, and when we reflected it across the line y equal x, we let those x values equal the y values. So the domain of the original relation became the range of the inverse of the relation. And similarly, we took the original range values, y values, and they became the domain of the inverse, the reflection. So each of these little ordered pairs, this -2, -2, 4, became 4, -2, interchanging the x and the y. The 0, 0 was the same. Why was 0, 0 the same? Because why? It's on the line y equal x. So if your x value equals your y value, if your y value equals your x value in your original relation, it doesn't change, right? Because it falls on that line. And then like maybe if I looked at this one -2 became -2, 1. So the x and the y values are interchanged between a relation and its inverse, its reflection across y equal x. So what if I were to give you, just like we did in the investigation yesterday, what if I were to give you this function, right? And it's a function, f of x. F is a function of x. What type of function is that? It's a linear function. How do we know it's a linear function? Because why? Okay, so the degree of x is 1, right? So then it's a linear function. So we should get the graph of a line. So we could just graph the line based on what we know, or if for any function that you've been given, if you have the rule and you don't know what the graph is going to look like, whether it's linear, quadratic, cubic, whatever type of function you've been given, you can make a table of values. Are there any restrictions on the x values that I can choose? No. So I can substitute anything I want, like -2, -1, 0, 1, 2. And if I were to substitute in each of those x values into that function, f of x equals 3x plus 2, what would I get as the corresponding output values? For -2, what would I get? For -1, what would I get? Oh, very special. For 0 and 1, and if x equals 2, y is 8. Okay, so I could plot those points and I could connect all those points and get the line. Or I could look at this equation and what is a good point I could start with to graph it? The y-intercept. And what is the y-intercept?
2.
No, I don't. That doesn't need to be an ordered pair.
0, 2.
0, 2, right? So I could plot the y-intercept 0, 2, and then from there, what could I do to get another point on the line?
You could go up 3
Up 3 and over 1. Apply the slope. Rise 3 and run 1. And then, or I could go down 3. 1, 2, 3, and back 1, right? So there's the original equation. So I'm going to label that f of x. So that's my original function. And you are being asked, and this is a very good problem, right? You're given a linear function. We're graphing the linear function. And what are we being asked to do? Find the inverse, right? We are being asked to find the inverse of this function. And so I'm going to go ahead and graph y equal x, but just because I like to see it. So I'm going to graph y equal x. So I'm going to plot all the points. And I'm going to graph y equal x. You don't have to, but I like to see it because it kind of lets me visually see what I'm doing. And then how would I get the points that fall on the inverse? And notice this little superscript here. So this little superscript kind of looks like an exponent. That little superscript of -1 says that I'm taking the inverse of the function. Now, we're going to talk a little bit more about that notation, but if I'm looking for the inverse, we represent, if you are given a function, let's say f of x, the inverse of the function is represented with this little -1 as a little superscript. This -1 is saying I'm taking the inverse of the function. And notice how it's attached to the f. We're going to talk a lot about how it is not written like this, right? So that little -1 is implying, don't come on the test and say, what does that little -1 mean? That means you're taking the inverse of the function or the relation that you've been given. You are reflecting its graph across y equal x. So how am I going to get points on the inverse?
You can start with -1, -1 being the point. It's on y.
Okay, so -1 doesn't change, right? Because the x and the y are the same there. I like that. And how am I going to get these other points, some other points on the graph?
You just flip them.
I'm what?
You flip them.
You interchange them, right? So my domain values become my range values, and my range values become my domain values of the inverse. So I can literally interchange the x and the y values. So when x is -4 is y is -2. Do you see how we interchange the x and the y values? Then we have 2, 0, 5, 1, 8, 2. So I could plot those points. So -4, -2. -1 is on y equal x and the original graph, so it's on its inverse. And then that y-intercept 0, 2 becomes the x-intercept 2, 0. And then we have 5, 1, and then we have 8, 2. So I could graph that, and I would label this as the inverse of x. And hopefully you see how each of the points, and this stays the same, is being reflected across the line y equal x. So that is, and label your axes so we don't lose any points, right? But that's a very good problem, being given a function and asked to write the, graph the inverse. Could we get the equation of the inverse? Do we know how to do that?
Yeah.
How do we do that? So if I begin with, and I'm going to change the f of x to y to prove
on the slope.
Okay, well, I could look at the graph, that purple graph of the inverse, and I could actually go from point to point, count the slope, and find the y-intercept. Is there a way to do it algebraically?
Yeah.
How?
You have two ordered pairs and x1 minus x2 over.
Okay, so you could find the slope of the line passing through the 2 points on the inverse of the function and then substitute it into point slope or slope intercept. But if I want to go directly from this equation, based on what Bryson was saying yesterday.
Put the x equal to the y, so like x equals and then the y in the equation.
That is correct. We literally are interchanging the x and the y values.
And then isn't it y equals 1/3 of x minus 2
Yeah,
over
we solve for y then. We solve for y. So does everybody see how we said, oh, let my range value in the original one become the domain values, and let the domain values, x in the original equation, become the range value. So you literally are interchanging the x and the y, and you're solving for y. So what would we do next? If I'm solving for y,
Put y on the other side.
well, the y is, why don't we isolate the y on the right-hand side? Subtract 2, and then,
By 3.
and divide by 3. So what would we get? We get y equals,
1/3 x minus 2/3.
that is correct. And no matter, I don't care how you get it, but they're going to become more interesting, so we might want to be able to do it directly with that instead, because they may not be linear functions, right? So let's look at the definition of the inverse of a function. So if we think back to when we were talking about whether a function was even, odd, or neither, if a function was even, there was something that we had to algebraically show to show that it was even, right? To show that f of x was even, we had to show that,
F of
F-
x equals negative, or f of negative x.
absolutely correct, f of x equals f of negative x. And if a function was odd, we had to show that that is correct. F of x equals negative f of negative x. Well, guess what? If I give you two functions, let's say I give you function f and function g, they're two functions, and I say they're inverses of each other, right? F is the inverse of g, g is the inverse of f. I could literally find the equation and say, yeah, there it is, but that's not verifying it. Right? For two functions to be inverses of each other, the way that you show that is that you show that the composition of each of the functions composed in different orders. So f composed with g and g composed with f, both of those equal each other, and they each equal x. Wow. Okay, so what is that saying in a nutshell? That's saying f composed with g, which can be written like that or this, and at g composed with f, which can be written in that notation or this notation, both have to equal x. So f composed with g of x equals g composed with f of x, and that equals x, right? It's not enough to show that these are equal. They both have to equal x. And this is true for every x in the domain of the inside function. And the out, to look at that, right? So the inverse of f of x, we said, is denoted with this little superscript of -1. And the domain of f is equal to the range of the inverse of its function. And remember, okay, are there any questions on what we did? All we did was formalize the activity that we did yesterday and add this new name, 1-to-1, meaning the original relation is a function and its inverse is also a function. Any questions on this? No? Okay, so you can use the rest of your time to work on any of the practice, the My Math Lab, anything that you need to do. On Thursday, we are going to do a little review activity. So hopefully you will have done all of the practice and come to tutorials. I will not be in tutorials today. I will be in tutorials tomorrow to answer any questions. Thursday is a review. I will be in tutorials Thursday as well. And when is your test? There you go. I'm going to point out this represents the inverse of a function. Now, why am I pointing that out? Because if we think back to when we were dealing with real numbers, right? Let's say I gave you 4 raised to the negative 1 power. That's just a constant raised to the negative 1 power. How do we rewrite that without a negative exponent? It would be 1/4, right? Which is the inverse of 4. However, that is not the same case when we're dealing with a function, right? So when I am given a function, f inverse, the inverse of f, that does not mean 1 over the function. Okay, so this is so important. A lot of people make that mistake. So if I were to give you a function and I were to represent f inverse of x, that does not mean 1 over. That means we actually have to interchange the x and y, and we have to find the inverse, the equation of the inverse. If you were to write it on the outside, that is telling you to take that entire function and put it in the denominator. So notation, 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 notation. We have to understand that this little superscript of -1 is implying that I'm taking the inverse of the function. I am reflecting it across the line y equal x. So let's say I give you 2 functions, f and g. So here is f, and here is g. And I want to show that they are inverses of each other. Again, I am not taking f, finding the inverse and saying, oh, there it is. Or I'm not taking g and finding the inverse and say, oh, there it is. It's the same thing. Instead, we must show this. So if you're given 2 functions and you're asked to verify that they are inverses of each other, the first thing that you write is, if f and g are inverses of each other, we need to show. And you will write this statement. If you do not write that statement, we need to show this. You're losing some credit, right? This is your justification. You can't just do work, right? We have to tell whomever's reading your work needs to know what you're trying to accomplish. So to verify f of x and g of x are inverses of each other, we need to show the composition in both orders equal x. So here we go. So let's see if we remember how to do this. So if I'm looking at f composed with g, so I'm looking at f composed with g, where the input is x, right? I can write it like that. How do I find the inverse? What do I do? How do I find the composition?
You substitute x in f of x for x minus 2 and 3.
Okay, so I'm going to start with the outside function, right? And I'm evaluating f of x at g of x. So everywhere I see an x, my input to my function f is going to be the entire function g of x. So I'm substituting in g of x in for x. So far, so good? Okay, and now all I do is simplify the right-hand side. So how do I do that?
Distribute the 3.
Okay, well, we could.
Or multiply by 3 and it gives you x minus 2.
That's right. I like that. See that you have a common factor in the numerator and denominator and simplify. You could have distributed the 3 and get 3x minus 6, right, over 3. But then we still have a fraction. So this is lovely. So what would this give me? X minus 2 plus 2, which is x. So we got this to equal x, right? So we're halfway there. Right? But we still have to show that g composed with f, where our input is x, is also equal to x. So let's go ahead and do that. So I start with my outside function, g of x. And everywhere I see an x, I'm going to input f of x, right? So f of x is what? 3x plus 2. And if I were to simplify that, what would I get? 3x over 3, right? Because the plus and the minus 2 sum to 0. And then I could simplify common factors from numerator and denominator. Those simplify to 1, so this just gives me x. So now I have shown that. So since f composed with g of x equals g composed with f of x, and they both equal x, since that is true, then f of x and g of x are inverses of each other. And yes, we're writing that final statement. So I hope you can do this problem from start to finish. That's a good problem. All right. Now we know what the inverse of f of x equals 3x plus 2 is. We just verified what it was. But let's algebraically show how we would get that inverse by interchanging our domain and range values. So our original function is y equals 3x plus 2. That's what we've been given. And I want to algebraically find the inverse of f. So the first thing we do is we interchange those x and those y values. So y becomes x becomes y. We solve for y, and what do we get? What do we get?
X minus 2
Over 3. Now, we are going to represent the inverse, right? So our original function was f of x. So we would write f inverse of x equals x minus 2 over 3, right? So we were given f of x, and we're finding the inverse of f of x, so that's how you would write it. Now, how could we verify it? How could we verify?
Take the inverse of that.
We could take the inverse of that and see if we get the original function. What else could we do? That is correct. We could show that the composition in both orders of those given functions equal x. Yep. So we know that taking the inverse of a function is a reflection across y equal x. We know what the notation means, what it means to show that we're taking the inverse of a function. We know what we need to show if two functions are inverses of each other, and how to represent the inverse of a function. So, what if I give you a graph, and, well, let's say I give you the first graph, okay? So that's a parabola, right? The blue curve is y equals x squared. Is that a function? Is the graph of y equals x squared a function?
Yeah.
Yes, it is. And you said, oh, I can just look at it and I can see it passes the vertical line test. Well, what if I wanted to take that parabola, the graph of that parabola, and I wanted to reflect it across the line y equal x? Now, in the patty paper investigation we did yesterday, we took the parent quadratic function and we reflected it across y equal x, and we got a parabola that is opening to the right. Wasn't that true? Wasn't that the reflection across y equal x that we got yesterday? Now, is the graph of the reflection across y equal x, is the inverse of the parent quadratic function a function? No. So you could take the original graph, you could reflect it across y equal x, and you could do the vertical line test on the image. Or I can just look at the original equation, the original graph, and perform the horizontal line test. So the horizontal line test states that if I can draw a horizontal line on my original graph and not pass it more than once, then the inverse of that graph is also a function. Vertical line test to determine if the original graph is a function. Horizontal line test tells you, is its inverse a function? So if I look at the first one, I see, if I draw a horizontal line, oh no, it doesn't pass the horizontal line test. So while the original graph is a function, y equals x squared, its inverse is not. If I look at the next one, we have the parent cubic function, which is a function, but is its inverse also a function?
Yeah.
Yeah, because I can draw as many horizontal lines as I want, and I'm never going to pass through the graph more than once. So the original parent cubic function is a function, and its inverse, which we know what that looks like, right? Based on what we did yesterday, right? That we know that's also a function. Can you give me an example of a function that passes the horizontal line test and therefore has an inverse that is also a function? Can we think of our library of parent functions that we've worked with before? Y equals x. Okay, that is, so something else. I mean, that's true. Y equals x, yes. Can we think of another function that we've worked with that passes both the vertical and the horizontal line test? Y equals 1 over x, so you're super fancy generally. Right? Can I draw a horizontal line and pass through anything more than once? No. Another one? Can we think of another one? The cubic function? Okay, so y equals the cube root of x. Yeah? So what does that look like? So if y equals x cubed, right, it would look like that. And the cube root function is that, right? We could have chosen y equals the square root of x. We could have chosen, oops, whoa, let's back this up. This is not true here. We're looking for, those were both good examples of ones that do pass the horizontal line test. I'm asking here, what does not pass the horizontal line test? Can we think of a graph, even a function, whose inverse is not a function? Y equals x to the fourth. That's beautiful. Y equals x to the fourth, which kind of looks like a parabola, and we'd plot points, right? What about another one? I like the absolute value function. That's the one that was in my mind. So y equals the absolute value of x, right? Passes the vertical line test, but not the horizontal line test. So these functions whose inverses are also functions, meaning the graph passes both the horizontal and the vertical line test, a function whose inverse is also a function has a very special name, and it's known as a one-to-one function. That for every x, there's only one y. For every y, there's only one x. These are known as one-to-one functions. So as you get further and further in math, you may be given some information and say, oh, here's a function. It's one-to-one. It's smooth. It's continuous. And they'll tell you all these properties of the original graph that will prove very important in the things that you can do to their equations. So knowing that a function is one-to-one, we know that the original graph is a function, its inverse, its reflection across y equal x is also a function. Only one-to-one functions have an inverse that are functions, okay? So here are some more examples. If I look at this first one, it's one-to-one, passes the vertical and the horizontal line test. This second example is not one-to-one, it doesn't pass the horizontal line test. The third one is, well, first of all, it's not a function to begin with, right? Because it doesn't pass the vertical line test. So you should be able to look at graphs and immediately be able to determine, is it a function? And is it one-to-one? Is its inverse also a function? So let's look at these 4 examples. Is the first one well, let's first say, is the first one a function? Yes, it's a function. Is the inverse a function? Yes, so it is one-to-one. Passes both the vertical and the horizontal line test. Second one, is it a function? It's a function, but is it one-to-one?
No.
Not one-to-one. It fails the horizontal line test. Right? And we're explaining why it's not one-to-one. Is the next one a function?
Yes.
Yeah, because what happens if those 2 points that were open are both closed? What if these are closed? Then it's not a function. What if one of them's closed? It's still a function. So yes, this is a function. Is it one-to-one? Not one-to-one. I mean, for heaven's sakes, that's a horizontal line. That's a disaster. Okay, and then let's look at the next one. Is the next one a function?
No.
It is a,
Yes.
Bryson, why you say no? It is a
Oh,
function.
wait.
Every x has only one y value.
The other way around.
Okay. Is it one-to-one?
Yes.
It is one-to-one. I challenge you to tell me there's a horizontal line that crosses that graph more than once. So you should be able to look at graphs and immediately be able to tell me, is it a function and is its inverse a function? Is it one-to-one? And if not, why not? Doesn't pass the vertical line test or doesn't pass the horizontal line test. So as we talked about in the investigation yesterday, when we looked at the parent quadratic function and the parent cubic function, not all functions have inverses that are functions. Sometimes we have to do something to those functions, restrict the domain so that its inverse is a function. So let's revisit this parent quadratic function. And again, if you can't automatically graph it because you know the points that fall on that graph, well, that's okay. You can make a table of values, but hopefully you can graph this rather quickly. We're just squaring, right? So for input 3, the output would be good, 9. And -3 would be 9. So based on symmetry, here's the graph of our parabola. And again, if you can't remember, you can always make a table of values. There are no domain restrictions. So we can get these values and plot those points. But hopefully by now in our career, we can graph a quadratic function rather quickly. All right, now, if I were to take the inverse, and remember this, if we zoom in, is really going below, right? If I were to take the inverse, again, I would interchange, and I'd get something that looks like that. And we see that the parent quadratic function is not one-to-one. That image, the reflection of that graph across y equal x, is not a function. The original graph does not pass the horizontal line test. The image does not pass the vertical line test. Can you tell me what the equation, just for kicks, of the inverse is?
Plus or minus square root of x.
Y equals plus or minus the square root of x, right? This top part would be plus, right? And this bottom part,
Can you do plus or minus x to the 1/2?
yes, you can. That's beautiful. The square root of x can be written as x to the 1/2. So instead of a radical expression with a rational exponent, that is absolutely correct. So we're okay with that. Now, I could actually tinker with this parent quadratic function, and I can restrict the domain of the inverse so that I do get a function. And I can look at the original part where we said, I'm only going to focus on positive square root of x, positive square root of x. And I'm going to get this. So if I'm looking at only when x is greater than or equal to 0, so not just positive but also 0, I'm going to get just this top half of the graph, right? And I'm looking at the image, right? So I'm looking at 4, 2, right? I'm looking at this. So that is just y equals the square root of x. Agreed? Is that a function? Yes. And where did that come from? That came from this part of the graph right here. No, it didn't. I lied. It came from this part, right? This part is being reflected over y equal x to get this. 0, 0 stays the same. 1, 1 stays the same because they're both on y equal x. But I could just as easily have looked at only this portion, restricting my quadratic parent function to when it's less than or equal to 0. And that would become, oops, I don't want to do that there. I want to do it down below. That would give me just this lower part. And what would the equation of that lower part be?
Y equals a negative square root of x.
That is correct. So I can restrict the domain so that when I take the inverse, I still have a function. So I could play with the pieces, right? If I needed to get information, I could play with the pieces by restricting the domain. Again, each of these are the result of reflecting across y equal x, which is taking the inverse. Prepare for the test. So you have lots of practice on taking the composition problems to. You have lots of practice with graphs. There's a little excellent primary, and there is a skills. These are review, and there's tons of practice.